Okay, so today we're going to look into numerical differentiation. So from your symbolic math, you were able to calculate the derivatives of functions and you were able to apply them in some physics problems. Okay, this time, how do we do differentiation using numerical methods? Okay, there are a lot of ways to do this, but we're going to focus first ourselves with one-dimensional differentiation. And we're going to use what we call the finite difference. Okay, so we're just after the concept of doing differentiation numerically. Okay, so first is, let me graph a function first. Okay, so say symbolic math, we're going to, okay, so let's say 25 minus f plot 5 minus excuse me 5 minus x limit our x-axis from 0 to 7 and the y-axis, let's say, from 0 to 30. Okay, so let's run. So this is your result. So let's copy this and then let's paste it here. Usually when we differentiate this, okay, so we want to differentiate function with this example. So this 10 minus 2x. Okay. Now for differentiating this, we can do this 3 ways. Okay, so as I mentioned here, we're going to focus on a finite difference. So that means the difference between 2 points is finite and it is the same for everything. Okay, so first is we can do forward. So let's say we want to calculate say this is x and this is y of f as a function of x. And say you want to calculate the derivative, let's say want to calculate the derivative at x equal to 3. So here. Okay. So you want to calculate the derivative here. Okay, so the first thing that you need to define first is that difference. So we're looking for what we call h. H is the difference, and we define this as xi plus 1 minus xi. So sometimes we call this your step size. Okay, so it is called forward because your xi, from your xi, this is your xi, you move forward with the next iteration. So let's say your h is equal to 1. So your next iteration or next value for x would be here. So this is your xi plus 1. And then you just pick the slope of this line. Okay, so the the derivative at xi for forward difference is approximately equal to the value of your function at xi plus 1 here. So this is f xi plus 1 minus the value of your function at xi. So this is your value of function at xi divided by h. So that's your forward difference. Okay, now this is very useful if you know your initial value. Okay, now we can do the same if you want to, we do the same for, let's say, a backward difference. Okay, so again, we have your xi here. So at xi, so you, instead of stepping forward, you're stepping backward, wherein this is your xi minus 1. So the value of f at xi is here. The value of f at xi minus 1 is here. So this is f xi minus 1. So our h here is xi minus xi minus 1. And the value of your derivative at xi is what? This is equal to, approximately equal to the value of the function at xi minus the value of your function at xi minus 1 divided by h. Okay, so as you will notice, if we're going to compare this, okay, the value of your derivative here would be equal to this if your xi plus 1 here is equal to xi here. You get my point? Okay, so this is backward difference. Now, this is useful when you want to find the derivative or estimate the derivative at the end of your function. Because you cannot use this at the beginning of your function because there is nowhere to step backward. Same goes here in the forward difference. You cannot use this at the end of your function because there's nothing after that end. Okay? Now, if we're going to compare, now, okay. There is now somewhere in between called center difference. So again, let's choose x equal to 3 to be our xi. Okay, so the derivative at this point, okay, so you're going to step forward at xi plus 1 and backward xi minus 1. So here we are centering your point where you want to calculate your derivative. So we're now going to look into the slope of this line. The slope of this line. Okay, so here, this is f at x minus 1. And this is f at x plus I. So our h here would be either xi minus 1 or xi plus x plus 1 minus xi. Okay, so either or, it's still the same because we're looking for a finite difference. So we are looking for equal spacing. But the derivative at xi will now be approximately equal to f xi plus 1 minus f xi minus 1, now divided by, because we're looking for this step, so this is actually 2h. Okay,